Okay, let me start by talking about the midterm exam on Monday. All right, so excuse me. The exam will be 45 minutes, regular class time right here, and it will cover basically from day one. So that would be what, week 0 Thursday? I mean, week 0 Friday? There, I would say week 3 Monday, which was kind of Monte Carlo estimation part 2. Okay, handwritten exam. It's going to be mostly I don't know, math-based. Mostly math-based and, I don't know, conceptual. So no R code. But you do you have to be comfortable with kind of all the algorithms that we've all the algorithms mentioned. Okay, and I'm trying to figure out how much to fit into the exam, but so I'll say possible problems. Okay, some, maybe all possible problems. Okay, so one, we might have you might have an inverse CDF problem. Okay, and I'll give you a PDF. So I'll provide a PDF. Okay, and you will figure out the CDF. Okay, and then you figure out the CDF's inverse. And then I will provide a random value u. And you tell me what random value of x it corresponds to. Okay. I don't know. All right, I'll go ahead and, like, for example, what if the CDF I give you, or the PDF, so this is, possible PDF, which is basically, this is not going to be the problem, okay? So you'll have 1/2 minus 1/4 x for 0 to 2, and it will be negative 1/2 plus 1/4 x for x in 2 to 4. Okay, and then this would be, pretty sure this was 0 to 4. Okay, so that that's a possibility. Try that out. Okay, another one. You might have, so another possible problem is rejection sampling. So I will provide the target distribution, PDF, f of x. I'll also provide a proposal, PDF, g of x, okay? And then maybe, so you need to figure out M, figure out the expected acceptance rate, I guess in the long run. Okay, I will provide a value y drawn from G. I also provide a u drawn from uniform 0, 1. And you tell me if we accept or reject y. So that's like a possible rejection sampling problem. Okay, so these are all just possible problems, not necessarily that this will happen, okay? Just possible problems. But I think things to kind of think about and study. Yes? Yes, you most definitely need a calculator. Graphing is fine. Not your cell phone, not a computer, not a tablet. Okay, just a regular non-internet connected calculator. Do the graphing calculators connect to the internet now? I'm sure some of them do. Okay, so no internet connected calculators, all right? Okay, another possible problem. Okay, so we maybe will have a Box-Mueller problem. So what would this be? So I would provide two values, maybe U1 and U2, drawn from uniform 0, 1, okay? And then you convert them to Z1 and Z2. Okay, or maybe a convolution problem. I provide some a series of U's, okay, drawn from uniform 0, 1, and then you convert to a random draw from maybe, we'll say, binomial with n and p, or maybe a beta with the shape parameters a and b. Okay, and so you need to know how to do something like that, right? So it's basically, I give you some random u values, and then you have to turn them into using kind of the rules for the convolutions, okay? So, I mean, this is too much to fit into 45 minutes. So the problems that will appear on the test will be a subset of these things I'm listing out, okay? Okay, and then we'll have a bivariate normal problem, maybe, okay? Possible, right? And then for this, I would provide Z1 and Z2 drawn from standard normal, okay, where Z1 is independent of Z2, okay? And then I'll say, you know, the goal is to have X coming from normal 2 with mean mu and standard deviation sigma, and then so you must find, and we'll define X as B plus A times Z. So you must find B and A, and then convert random draws Z1 and Z2 to X1 and X2. Okay? Bye. Is that okay? All right, and then the last potential problem would be, I'll call this very bad Monte Carlo estimation. Okay, and then so okay, so I'll provide, so you want the expected value of f of h of x, okay, so I'll provide h of x, okay, and I'll provide a simple f of x, okay, and then I'll provide like maybe like 3 u's drawn from uniform 0, 1, okay? I'll say this, okay? I'll provide 3 draws of u, okay? And then and based on that, you'll need to figure out your random x's based on f of x, okay? So you'll need to, am I telling you too much? Okay. No. Of course you say that, all right. So you'll need to, you know, figure out the x from the u, okay? And then step 4, profit, we got to estimate this. What's going on? Estimate E of f of h of x, okay? Based on your 3 random values. Okay, so it's just a small scale version of Monte Carlo estimation, but on the computer you would do like ask for 10,000 values or 100,000 values. Obviously, because you're doing it by hand, I'm only going to give you like 3, okay? Okay, and each of these things, these random values u are probably going to be just out to like the hundreds place, okay? Just to keep things simple. Okay, are there any questions? How many do I have listed here? 1, 2, 3, 4, 5, 6. Okay, so in my opinion, all right, so that I'm guessing, okay, this should take about 12 minutes. Rejection sampling would take about 12 minutes. Box-Mueller, like 5 minutes. Convolution, about 5 minutes, okay? Bivariate normal, this might be like 10 minutes. And Monte Carlo estimation, maybe 15. Okay, so that adds up for too much. But, so this is kind of, so when I'm structuring the test and I'm aiming for around 45 minutes, this is probably, don't get mad at me if like I pick things and they add up to like 49, okay? but this is kind of what I have in my mind for how long each of these things would take, okay? Like the Box-Mueller thing, if I give you some U's and I ask for Z's, like if you know how the Box-Mueller works, I feel like it's pretty quick, right? You just make it exponential, take the square root, multiply it by r cos theta. Okay, all right, never mind. Something like that. Okay, questions? We already spent half our lecture talking about this, but okay. Is this good? We're gonna ace our exam on Monday. I was hoping for more confidence, but okay. I would recommend studying with friends, and like if you get a group of friends together, like each of you make up a practice problem and then give it to the other members of your study group, and then you all solve each other's practice problems, okay? So like one person will be assigned to the Monte Carlo estimation problem, and then that person's responsible for making like 2 different practice problems. Someone else is in charge of making a rejection sampling problem or something, and come up with two problems, and everybody practices on each other's problems, and then I think you'll learn. And then the attempt, the actual task of creating a practice problem is also very beneficial. So you're like, oh, I didn't get to practice rejection sampling. I promise you, if you had to come up with a rejection sampling problem yourself, like you will learn rejection sampling. So I'd say that's my recommendation. Get into a group of like 4 people, 5 people, whatever, 4 people or so. And then, you know, whoever's doing Box-Mueller and convolution problems should do both of those things, okay? And the bivariate normal. These 3, like one person can probably make 2 versions, 2 examples for all 3 of them. Okay. Okay, so that's that. Any other questions before I move on? Yes, question?
Partial credit on problems.
Yeah, if it deserves partial credit, yeah. Okay, so yeah, right. Show your work, okay. And if I can follow your work, and see where you've made a mistake, you know, we'll try to figure out what deserves partial credit, okay? So for example, if I don't know, for this convolution thing, you know, you made a small mistake in figuring out your binomial, you'll get some partial points, okay? You're not gonna get full credit, but partial points, yeah. Is that a question? Yeah. Just stretching, okay, it's also good. It's good to stretch our muscles. Okay. All right. Let's see. We got 25 minutes or so left. All right. So I'm going to just start to introduce our next, I don't know, segment here. Okay. So we've covered just we've covered a bunch of random variable generation things, right? So we said, like, we want to be able to generate random variables, and we got the inverse CDF and the rejection sampling and all of these other things to get random variables or random values drawn from a distribution. And then we said that's useful because we can do Monte Carlo estimation with our random values. We can, like, take the average of our random values, and that's going to be the an estimate of the expected value. Or we can take, you know, apply some other function h of x, and you can figure it out there, right? So we're going to take like a detour, and one of the most useful applications of Monte Carlo methods is in the context of Bayesian statistics, okay? And so I don't think anyone's taken a Bayesian statistics course, but I'm just curious, has anyone taken Bayesian statistics? No, okay. Or read up on Bayesian statistics? A little bit? Okay, all right. But generally, at this point, probably you've only encountered kind of frequentist statistics, okay? And but Monte Carlo methods are extremely useful, and you know, we'll learn some of the things later. But they're extremely useful in the context of Bayesian statistics. So I want to take some time, you know, next week, you know, today and next week, covering kind of the core concepts of Bayesian statistics, and then we'll learn additional Monte Carlo methods that are particularly well suited for Bayesian statistics. Okay, so okay, think back to your intro stats class, which was almost certainly a frequentist statistics intro stats class, and think about the topic of confidence intervals. Okay? You guys remember a confidence interval? All right, so let's say you make, so this is, all right, so we'll just do intro to Bayesian statistics. Okay. This is going to be our topic here, and we'll do this next week. Okay, so think back to your intro frequentist statistics class. Okay, and then so you probably, well, I don't know how you guys learned intro stats, but when I teach intro stats, we'll cover descriptive statistics and then some probability, and then we talk about the normal distribution, and then we talk about the sampling distribution, and then once we establish that the sampling distribution follows a normal distribution, then we can start making confidence intervals. Okay, and so if we make a confidence interval, let's say a 95% confidence interval for mu goes from 95 to 102. Okay, what is the correct statement we make about mu? We would start off with something like, I am what? I am 95% confident that mu is between 95 and 102. Right? Okay, and so what does it mean to be 95% confident that mu is between 95 and 102? Why did we have to use this phrase, I am 95% confident? Why did we not say there's a 95% probability that mu is between 95 and 102? Okay, so I don't know if your intro stats teacher told you this, but I try to make a point of it and say, when you make a confidence interval, one thing you are not allowed to say, at least in frequentist statistics, is to say that there's a 95% probability that mu is between 95 and 102. Okay, so in frequentist stats, you cannot say there is a 95% probability that mu is between 95 and 102. Right? Was this at least emphasized in your intro stats class? Yes? Okay. All right. And what is the reason why we cannot say there's a 95% probability that mu is between 95 and 102? Yes? Because it is or it isn't, right? We said that mu is either in this interval, 95 and 102, or it's not, okay? Because in frequentist statistics, mu is a fixed value. It is determined, and it doesn't make sense to talk about probability in that way, okay? I like to use this example and say, I've got this coin here, and if I were to flip this coin, okay, before I flip the coin, what's the probability that the coin will land heads? 50%, right? 0.5, okay. So I flip the coin, and then if I ask you the question, what is the probability that the coin has landed heads? What's your answer? So if you hesitate to answer, then that's correct, because once the coin has landed, there's no probability associated with it anymore. It either landed heads or it didn't. You don't know how it has landed. You don't know how it has landed, but you cannot say there's a 50% probability that the coin landed heads because it either did or it didn't. You can only say, I am 50% confident that it landed heads. Okay? You can say I'm 50% confident it landed heads, but you cannot say there's a 50% probability that it has landed heads because it either did or it didn't. Okay? So in the same way, mu, in frequentist statistics, mu is a fixed property of the population. There is no uncertainty about it, or uncertainty associated with it. Okay? We do not know what it is. Okay, but it is wrong to say there's some probability associated with it. Okay, mu is either in this interval or it's not. There's no probability associated with it. That's frequentist statistics. Okay. And so the idea is, if we were measuring, I don't know, let's say this was a confidence interval for IQ scores or something. If we wanted to, we could imagine a scenario where we freeze time and we somehow measure everyone's IQ scores, and then we average everybody in the population their IQ scores, and we get some exact value. That would be the exact value of mu. Okay. All right. In Bayesian statistics, we know we do away with this this central tenet that exists in frequentist statistics. We say the parameter of the population is not a fixed value. We say the parameter of the population itself is a random variable. It's a random value. Okay, so this is the key difference. In Bayesian statistics, the parameter of a population is not a fixed quantity. Okay, so like mu itself is a random variable. And so there will be a probability distribution associated with mu. Mu itself is a random variable, so mu has its own probability distribution, or whatever parameter it is that you're talking about. Okay? Whatever parameter it is that you're talking about, there is going to be a probability distribution. Okay? Mu, or whatever parameter we have has a probability distribution. Okay. Is that all right? And so the probability distribution associated with a parameter is going to be known as our, quote, beliefs about the parameter. Okay, so the probability distribution associated with a parameter. So again, parameters are properties of the population, but now we're saying that parameter itself is a random variable. The probability distribution associated with a parameter represents our, quote, beliefs about the parameter. Okay, so let's just kind of do a contrast, right? Okay, so frequentist statistics. You might have, do you guys remember maximum likelihood estimation? Okay, so let's say there's a coin. We have a coin. All right. And we want to know what is the probability this coin will land heads. This is what we want. What is the probability that the coin will land heads? Okay, so I do, what do I do? We're going to collect some experimental data, right? Okay, so we collect experimental data, and how do I do this? With a coin. I flip the coin. How many times should I flip the coin? Let's say it's really expensive to get access to this coin. So we're only going to flip the coin 10 times. I flip the coin, I flip it 10 times. Okay. And, all right, so that's basically 10 Bernoulli trials, right? Okay, and then let's say the results are heads, 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 tails, heads, tails, 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 heads, heads. How many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so let's say this is what I get. Heads, 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 tails, heads, tails, 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 heads, heads. Okay. 10 flips. These are my results. Okay. So now, based on our data, what is our maximum likelihood estimate of P? P being the probability that the coin will land heads. Okay, well, so how would we do this? We would have to calculate the likelihood of the data, right? Likelihood is going to be equal to what? If the probability that the coin lands heads is P, what's the likelihood of our data? We would go P times P times P for our first three heads times 1 minus P times 1 minus, right? I'm just multiplying the probabilities of each of my outcomes. Okay? This is the likelihood that we would get this result, okay, which simplifies to P to the 6th and 1 minus P to the 4th, right? Is everyone still with me? Okay, and then we want to find the value of P that maximizes this, right? Find the P that maximizes this, right? Okay, so we want argmax P of P to the 6th, 1 minus P to the 4th, okay? And this is hard to work with. So what's the trick that we often do? We take the log, right? Because we got powers to the 6th and powers to the 4th, and I don't know how to do derivatives and stuff like that. So so we take the log and it turns our powers into multiplication and addition, okay? So the argument that will maximize this, right? So the value of P that maximizes this is equal to the value of P that maximizes the log of P to the 6th, 1 minus P to the 4, okay? And so the value of p that's going to maximize the thing on the left will be the same value of p that maximizes this, okay? Of course, the things look different, but we're just going for the value that maximizes this, right? So we get 6 log p plus 4 log 1 minus p, okay? And then what do? We want to find this maximum, find the p to maximize. So we take the derivative, right? d dp, and we're going to get 6 over p plus 4 over 1 minus p times negative 1, okay? And we set that equal to 0, right? So 6 over p is equal to 4 times 1 minus p. And we get 6 times 1 minus p is equal to 4p. 6 minus 6p is equal to 4p. 6 is equal to 10p. 0.6 is equal to p. Okay, so this is the value of p that maximizes log of p to the 6th, 1 minus p to the 4th, and likewise p to the 6th, 1 minus p to the 4th. Okay, so our MLE estimate is p equal to 0.6. Okay. Are you guys satisfied with that? So we have this new coin. You look at it, I don't know. You say, all right, what do you think is the probability this coin's landing heads? They let you flip it 10 times. It lands heads 6 times out of 10. So you say, okay, I'm guessing p is 0.6. Does that sound reasonable to you? You guys are nodding your head just because I did math, but it shouldn't, right? I've got a nickel here, okay? What do you think the probability is that this is going to land heads? It's not a trick question. 0.5, right? Okay. And then, what do? I flip the coin 10 times, okay? We're going to pretend I did this, okay? And I record this, and it lands heads 6 times out of 10. Are you going to go home now and be like, ooh, magic nickel, it lands heads probability 0.6? No, right? But that's what you guys just said right here, right? No. What are you guys thinking? You're going to just say, oh, well, you just happen to get 6 out of 10. It's not a big deal, right? I'm not suddenly going to say my guess for the probability that this coin is going to land heads is 0.6, right? Even though, according to all this work that we did in maximum likelihood estimation, where we're trying to maximize the likelihood of our data, says that p should be 0.6, okay? We're not going to do that, right? Because in our brains, we have a mental picture of how a coin should behave, and whenever we have deviations from that mental picture, if that deviation is not severe, we're going to just say, my idea of what a coin is still the same, and these deviations can be explained away by chance. Okay? And it's only if the data that comes in is like significantly different from what I'm expecting, right? Like how many times would I have to flip this coin for you to be convinced that the proportionate lands heads is significantly different from 50%? If I did it 100 times and it landed heads 60 times, would you be convinced? What about 200 times and 120? 300 times in 180, 1,000 times in 600. Okay, so somewhere between 100 and 1,000 people will start becoming convinced, okay? And that's fine. And hold on, you guys. But that reflects Bayesian thinking, okay? In frequentist statistics and in our intro stats class, we teach you all of this stuff. But I think our natural tendency is to think in the Bayesian way, which says we've got an idea of how this coin should be in the first place, and it's only after a ton of data comes in that we start to question our original beliefs about the coin, okay? And so here, I guess we'll talk about the frequentist for now. On Monday, you guys take a test. On Wednesday, we'll come back to this, and we'll get more into Bayesian stuff. Okay, have a good weekend. Good luck studying. I highly encourage you guys to study in groups, and we'll see you guys on Monday.